Start spreading the news. It's calculus time. I want to be a part of it. Pre-calc. How we doing, folks out there? Another pre-calc video. Let's get right into it. Start recall. It's that word that starts with R, okay? We talked about yesterday, the indefinite integral. So recall the indefinite integral. You want to talk topic sentences? We're just doing the indefinite integral day 2, okay? It's just basic integration day 2 today. Get a little bit of practice in there. But remember, if you integrate a function f of x with respect to x, there's no implied mathematical notation for when you take an integral. A lot of people say if you integrate little f, you get big F back. Don't forget to put that c right there, that plus c. There can always be some constant you take the derivative of and get 0. Remember, that's somebody's derivative in there. Whose derivative? The answer's derivative. So what I have written right here is not good enough, okay, because it's not implied that if you take the derivative of big F, you get little f back. It's not the way it works. So we got to put that disclaimer and say where if you take the derivative of big F of x, you get little f of x back. And all that states is that you integrated correctly, okay? If you take the derivative of your answer, you'll get back what you started with. A way to avoid that is to say, let's actually integrate f prime of x with respect to x. Remember, that's somebody's derivative in there. Whose derivative? The answer's derivative. Geez, I wonder what I take the derivative of with respect to x to get f prime of x. How about f of x, Poppy? Plus c, okay? So if you do it this way, you actually don't need the disclaimer. Cool way to do it. We'll talk about that a little bit more next year. Don't forget about those, basic integration rules. So basic integration, much like O'Doyle rules. So you might get that movie reference. Maybe your parents get that reference. I understood that reference. Thanks, Cap. Okay, and we'll say the list, much like my waistline, will grow, but not today. And this is if you take the integral of one single letter raised to numerical power. Maybe it's not one single letter, though. That's why we call it u. It will be one single letter until tomorrow. On the integral of u to the n with respect to u, rewrite the base, add 1 to the exponent, divide by that number. Add some cookies, man, some cookies. But make sure you say that n is not equal to -1. Otherwise, you'd be dividing by 0. There's another way to take an integral if that's the case, okay? You had your homework, all right? I hope that you tried it. Hopefully not too terrible here. Did anything strange happen with the first 3 problems? I don't think so. You can see you could break up derivatives, integrals, and derivatives for that matter. But integrals in this case over addition. Just pull the 2 to the side. Integrated x to the first, got x squared over 2, brought down the addition sign, and I said, what do you take the derivative of with respect to x to get 3 back? That would be 3x. Don't forget to put that plus c on the end. Don't forget to put things in form that you want to integrate them in, like making 1 over x squared into x to the -2. And this one over here, 11, which is what really loud amplifiers go up to, I decided to actually rewrite a bunch of these terms, actually just one, before I actually took the integral, and then simplifying, always important, okay? You might have slightly different answers. You could certainly have x to the 4th over 4. They might write that. Here they might write 5x squared over 2, 4x to the 5/3 over 5. They'd probably write this way, but every now and then you get a negative exponent in there, so minus 2/3 x to the -3 could happen. Make sure you can manipulate, all right? There's some try problems here. I actually whited them out, rewrote them over here. We will try them in a second. Maybe you already tried them, but I wanted to discuss something about 7 and 9. 7 and 9, they aren't in a form for basic integration, okay? Here, the base of a numerical exponent is not one single letter. If this was just one big X that was being squared, then it would be basic integration. Just like here, if this is just one big X that was being squared, then it would be basic integration. To turn it into basic integration, you could double bubble it. Right now, this is not basic integration. You can't break up integrals over multiplication, okay? So you can't just integrate one, then multiply by the integral of the other. It's not the way it works. You need to actually FOIL or double distribute out. Then they're both in the term where you could use basic integration, in a form when you could use basic integration. Some people don't like that. They're like, you know what, Berto? I'm just going to treat this x plus 1 like he's one single x, and I'm going to rewrite him. I'm going to add 1 to the exponent, and I'm going to divide by that number. Then I'm going to plus c. That's my answer right now. Believe it or not, that's correct, okay? And some people are like, well, how do I know if that's correct? Well, remember, if you take the derivative of your answer you'll get back what you started with, right? You could always check by taking the derivative. And really, once again, they're just treating this like it's an x squared. Technically, that's what the outside function is. It's a composite function. To take the integral of x squared, you rewrite the x, add 1 to the exponent, divide by that number. It's just not, you know, an x that's the argument here. It's an x plus 1. Well, let's do the check and make sure this is all right. So let's take the derivative with respect to x of this guy right here. And if you don't mind, I'll write him as 1/3 x plus 1 quantity cubed plus c. And if you actually take this derivative here, you got to use the chain rule. Drop the 3 like it's hot. 3 times a third is 1. Rewrite the entire inside. Raise the exponent to the 1 less. But then you got to multiply by the derivative of the inside. But the derivative of x plus 1 with respect to x is just 1. Then the derivative c is going to be 0. Derivative of constant is just 0. And this is just a really complicated way to write x plus 1 quantity squared, which is what my integrand was. So apparently, if you triple bubbled this out and simplified it, you would get this. Most likely, you might end up with a separate constant when you triple bubble this out. Then you need to combine that constant with c, so it'll just be another constant. I'm not going to get into that because that's a little too much right now. But if you saw it this way, it works. But cuidado, caution here. If you're going to do something like this, I don't suggest it because the only reason it works, is that how you spell that? Was there like an upside down question mark there or something? I never understood that. Never understood any language besides English. I'm not even good at that. Sheeple, give it a gobbledygork. Anyway, this only works because the derivative of the inside is equal to 1. Look over here. The derivative of the inside is not equal to 1. It's actually equal to 2. So this method would not work. If you did the integral of 2x minus 3 quantity squared with respect to x, and you want to just treat, you know, the 2x minus 3 like it's one single x and say, I'm just going to add 1 to the exponent, divide by that number, add some cookies. This is incorrect, okay? Incorrecto. And if you try to check it out, you'll see what we're talking about. If we take the derivative with respect to x of, you have 1/3, 2x minus 3, quantity cubed plus c. Now when you take the derivative, 3 times 1/3 is 1. Rewrite the inside, 2x minus 3, raise it to the 1 less, that's 2. But now multiply by the derivative of the inside, and the derivative of the inside, that's 2. And then you add the derivative c, which is just equal to 0. This gives you back 2 times the quantity, 2x minus 3 squared. And this thing right here is not the integrand, okay? So be very, very careful. This is only going to work when the derivative of the inside is equal to 1. These tomorrow will become U substitution situations anyway, so you probably won't even integrate them by using what I'm doing right here. But this could be useful. You know, if something's not basic integration, sometimes by performing an algebraic technique, you could turn it into look like something that's basic integration, okay? And that can become very powerful because we'll talk about U substitution tomorrow, but U substitution will not always work, all right? So something cool to talk about there. You know you thought that was cool. Search your feelings. You know it to be true. That's what happens when you have 2 daughters, by the way. You just end up using cups that have like Disney princesses on them. And I know who they are too. You got Snow White over here. God, that's got to be Rapunzel, right? Or maybe that's Belle from Beauty and the Beast. There's Jasmine, right, from Aladdin. Who else we got? That's Cinderella, right? The most famous Disney princess. That was my daughter's favorite until Elsa. This right here is Belle, okay? So this must have been Rapunzel over here. I'm losing my mind. All right, so let's move on to the try problems here. Okay, do or do not. There is no try. Yoda, kind of harsh, okay? Over here, the integral of x cubed plus 6x squared quantity over x with respect to x. People are like, hey, let's just integrate each thing separately. No, you can integrate over addition, but you can't integrate over division, okay? And there are several different ways to do this here. A lot of people will think to actually factor an x out of the top, which is a great idea, I won't lie, and it probably works out the best in this case, because then you can just cancel these x's out and really just integrating x squared plus 6x. Believe it or not, if there was an x squared downstairs, that still works. If there was an x cubed downstairs, then factoring isn't really going to work the way you might have thought. There are several things you could do. You can make x to the -1, bring them upstairs, distribute him. But try to remember when you have multiple terms, connected by addition or subtraction, which they have to be if they're terms, over a monomial, you could do a little many over 1 action. Do you remember that? Nice little heart. Okay, split the divisions right there. It's extremely important, and it'll work more often than factoring and canceling works. In this case, it doesn't matter, because here you just have x cubed over x plus 6x squared over x. And this is important stuff. If you just write this, you're totally wrong. You forgot the dx. Not only that, you turn a quotient into a quantity. You need parentheses. They look for stuff like this on the AP exam. You got to pay attention to notation. We know x cubed over x, by the way, is just x squared plus 6x squared over x is just 6x, what you want to grow up to be. And now we have exactly what we had over here when you factored and canceled. Wow, my daughter's making a lot of noise up there. Anyway, so I'd focus on many over 1 because it's going to be a lot more useful. You'll see what I mean than factoring and canceling, but they're both viable. And now, gee willikers, Batman. Basic integration, right? Connected by addition. I know the integral of x squared is x cubed over 3. Plus, to integrate 6x, 6 is a constant, connected by multiplication, pull them to the side. Integrate x to the first. Just add 1 to the exponent, divide by that number. And don't forget to add some, maybe instead of cookies, maybe crustaceans, right? A little bit of lobster or crab or something like that. Some people are like, ew, I hate lobster. Those people don't know how to live life. That's all I got to say. Anyway, I'll turn this into 1/3 x cubed plus the 6 divided by 2 is 3, so 3x squared plus c. Nothing wrong with writing x cubed over 3 instead of 1/3 x cubed. Regardless, a lot of different ways to write these. Just like number 2, this is not in the form to integrate. You got division here. We're going to get rid of this division by rewriting this thing. You could say 1 over x to the 1/2, but then bring that x to the 1/2 upstairs. X to the negative 1/2. You should know these things are equivalent, and it should be quick, okay? You need to be able to move fast and efficiently in here. You know, now we can integrate. We just have, you know, one single letter raised to a numerical power, add 1 to the exponent, divide by that number. Negative 1/2 plus 1. I can't do that. Well, first off, you should know that's equal to 1/2 just from common sense, okay? But a convenient form of 1 here would be 2 over 2. Then it's pretty easy to see that it's equal to 1/2. So x to the 1/2. Now look, Dan Rourke, he's going to divide by 1/2, okay? But the rest of us, we're going to multiply by 2 over 1, right? Multiply by the reciprocal. You don't need to go to that right away. You could just show the other step, you know, dividing by 1/2. Same thing as multiplying by not just 2 over 1. How about just 2? And how about taking the x to the 1/2, making it radical x? I forgot to put a plus c over here, and let's do that, and then bring the plus c down here. All right, so you got to practice these, okay? They might seem simple, but I'm telling you, integration is weird, man. Unless you practice it, you are going to run into trouble, okay? You know, let's do the other problems from the homework ditto, okay? So it's really just more practice. So if you want right now, you could just put this video on pause. Do 2, 4, 6, 8, and 10. Don't do 12. 12 is going to be for homework. Also, this problem for homework, the integral of t radical t with respect to t, add that to your homework as well. So if you want, you could pause and try those problems. And then when you hit the play button, we'll be right back here, okay? And we're back, okay? So if I want to integrate x squared plus 1 with respect to x, very simple to do. I can break up integrals over addition. The integral of x squared is x to the 3rd over 3. Plus, the integral of 1 with respect to x, if you broke this into 2 integrals, which you wouldn't, it's silly to do. Sometimes you need to do that. It would look like this. It's really just the integral of dx. We talked about that. It's x plus c. Or how about this? That's somebody's derivative in there. Whose derivative is 1? It's x's derivative, okay? If that was a dt, then you would actually have a t right here, not an x, okay? The derivative of x with respect to x is 1. The derivative of t with respect to t is 1. So just be careful. Make sure you match the variables up. Then put that plus c. And whoop, there it be, okay? You know, speaking about variables, matching them up, number 4, we have integrating in terms of t, which is great because there are t's in here. If these were x's, if this was 3x squared plus 4x minus 6, and you want to integrate it with respect to t, that's madness. You can't integrate x with respect to t. I know you could differentiate with respect to a variable that's not even present, but you can't really integrate with respect to a variable that's not even present. That gets a lot more complicated. Anyway, so over here, just think about these as 3 separate integrals. The integral of 3t squared, pull the 3 to the side. The integral of t squared, add 1 to the exponent, divide by that number. T cubed over 3 plus 4 is a constant connected by multiplication, pull them to the side. If you split it into 3 separate integrals, you really bring them out, bring them out, bring them out of the integral sign. But here, we'll pull the 4 to the side. Integrate t to the first, right? Add 1 to the exponent, that's t to the second. Divide by that number, minus, and the integral of a constant. Remember, if you get tricked out with integration, try to always remember my voice in your head. That's somebody's derivative in there. Whose derivative? The answer's derivative. So what do you take the derivative of with respect to t to get 6? If you put 6x, doesn't this just look wrong? Okay, there are t's, and all of a sudden there's an x right here. I mean, t. This is getting way too dramatic. Look, the integral of 6 with respect to t is not 6x, it's 6t, okay? Because if you take the derivative of 6t with respect to t, you get 6 back. So be careful with that. It's easy to make silly mistakes. This actually becomes what? Just t cubed plus 2t squared minus 6t plus c. Can you hear my daughter screaming up there? Anyway, you know, so that's what my answer would be. So try not to let the variable mess with you. You know, number 6 right here, it's not really in the form to integrate yet. It's basic integration because the arguments of the functions are only one single x here. But I'd probably rewrite this as the integral of x squared minus x to the 1/2 quantity with respect to x. Some people eliminate the integral sign there. What are you doing, Poppy? You didn't even integrate yet. Okay, now I'm going to integrate, which means now I drop the integral sign. Integral of x squared, add 1 to the exponent, divide by that number, minus the integral of x to the 1/2, add 1 to 1/2. 1/2 plus 1 is 3/2. Rourke over there is dividing by 3/2. The rest of us multiply by 2/3. Then we put a plus c after it. Man, I'm just going to box that in right there. Okay, you can see how quickly we did that. Put in extra steps if you need to. But eventually, you want to get good like this, okay? And it only will come with practice. I'm telling you right now, if you do not practice, you know, integration, you're not going to get good at it. Even really good, smart people, okay, in this class who really understand stuff that I say right away, please, you know, practice the mechanics. There's going to be a lot of nasty algebra in there sometimes, too, and that's something you guys don't have as much of because of Common Core. Practice, 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 practice. I mean, we talking about practice, man. We talk about practice. Please practice. It's practice. It's not just a Klingon moon. Oh, sorry, that's praxis. Anyway, so here, the integral of x to 2/3 with respect to x, number 8. Hey, this is in form to basic integrate, right? You know, it's one single letter raised to numerical power. Let's add 1 to the exponent. Remember, if you're struggling with 2/3 plus 1, just put 1 in a convenient form of 3/3. So 2/3 plus 3/3 is really 5/3. Okay, so we get 5/3. Hey, you could divide by 5/3 if you want to. Claffey will probably do that. But the rest of us, we'll just multiply by 3/5 because we're too cool for school. That's why we're not there. Plus c. Okay, and then we'll box it in right there. It's not true. I'm not really too cool for school, as I'm sure Connor Crowley will tell you and scream that I'm a nerd. But newsflash, so are you, Connor, if you're taking this class, and so are all of you listening. And there's nothing wrong with that. Nerds are great people. We're not too cool for school. We're too school for cool. Except me, because I'm also cool. All right, anyway, you know, moving on to number 10 over here. Probably a good rewrite. We got y's here. People are like, why y? Because there's a dy right there. Okay, so that's why we have y's. I'm going to get a rewrite first, though. Because the cube root of y is really y to the 1/3. If you don't remember that, use it in trouble. Okay, plus 1 over radical y is 1 over y to the 1/2. Bring that upstairs, y to the negative 1/2. So, like, it's not calculus. People are like, yeah, I struggle with that. Calculus is difficult. This is not calculus, okay? It's not even pre-calculus. It's algebra, okay? Come on. All right, so here, let's integrate now. Add 1 to the exponent, so 1/3 plus 1. Same thing as 1/3 plus 3/3. That's going to be 4/3, right? Okay, Claffey will divide by 4/3. Let's multiply by 3/4. Plus y to the, add 1 to the exponent, okay? Negative 1/2 plus 1 is positive 1/2. Instead of dividing by 1/2 like Shalene would do, let's multiply by 2. Flanagan multiply by 2 right away because Flanagan's pretty cool. All right, plus c. All right, and that's actually not a bad answer at all. You know, maybe they write it as 3y to the 4/3 over 4. This is kind of silly. I like this one better because if you want to take a derivative to check, this is a better form. But there's nothing wrong with that. What they have right here, those y's and those 4's, so terrible with my y's. They can look like 4 sometimes, so I'll try to enunciate a little bit more. Plus, you can make this 2 radical y plus c. But once again, lots of different ways to actually write these things up, okay? You know, so please practice this stuff, okay? You know, extremely important, like I said. And tonight, try that homework, okay? Tomorrow, we'll talk about use substitution. We'll get into that, and then we'll use that for some more basic integration rules we'll do on Monday and Tuesday of next week. Wednesday, a little bit more, right? And then Tuesday, and maybe Thursday, and maybe Friday, could be working on the test, or just Friday working on the test. Maybe Monday. I got to figure it out. I got to see what I'm doing. But Monday, you guys might have APs. I don't think so, though. I think that's just Gov. And Tuesday's calculus, so you should be all right with Monday and Tuesday. But then again, they're changing up times and stuff. So I'm going to try to give you that 2-week period for APs. Just give you a big, like, you know, final review, a bunch of problems to do over 2 weeks. It won't take nearly that amount of time. But I want to try to help you guys out. But if I do that, you better be right back and ready to rock after APs. Don't be giving up. Look, if you're seniors, look, I understand you're off to college next year, but come on, this is not an AP class. This class is still ongoing after APs, and juniors don't even start, okay? You got a whole nother year of high school. These juniors after APs, they're like, oh, I'm done. I don't want to do anything. Who do you think you are? All right, so I know right now the juniors are giving me a face, and the seniors are like, yeah, Berto, that's what I'm talking about. Anyway, I guess that's it for today, okay? So we got integration, basic integration, day 2. Don't forget about the indefinite integral. That's somebody's derivative in there. Whose derivative? The answer's derivative. Don't forget about those basic rules, okay? And you might have to put things in a, form to integrate before you actually integrate, all right? So try that homework. Hope everybody's safe and healthy. I hope to see you soon. It's not looking really that great that I'll see you soon, but you never know what's going to happen, okay? And at the very least, hopefully I'll see you next year, and we'll rock and we'll roll out of control. This is Berto signing off. Have a good one, folks. Adios.